industry and went into the solar instead. But first question, in order to kind of establish a baseline is, what is the wind? Basically, in its simplest terms, wind is the air when it moves from from a area of high pressure to an area of low pressure. It's created in two different ways. First of which is the uneven heating of the Earth's surface. If the sun's hitting the lake, it's going to heat up at a different rate than it would if it was hitting a forest or a pasture. So there also, the fact that the Earth is moving gives a certain spin to the atmosphere. So that's, in essence, that's where wind comes from. The fastest recorded straight line wind was recorded at 231 miles per hour on Mount Washington in New Hampshire in 1934. The fastest wind ever recorded was 301 miles per hour, fastest wind on Earth that was ever recorded was 301 miles per hour, measured in 1999 with a tornado in Oklahoma. We measure the wind in a number of different ways. Most meteorologists use meters per second. That's generally what you hear in the wind industry. A lot of national weather services, they use kilometers per hour, and then sailors tend to use knots or nautical miles per hour. Okay, there's going to be a quiz later. Basically the conversion factors there are right in that little box there. Take note. All right. How much of the wind can we harvest? The Betz limit basically is a theoretical limit to how much of the wind we can actually capture and transfer into energy. Basically, the wind passing by the blades that causes them to spin is where you get your energy from that rotational force. Okay. If you tried to capture all of the wind, you wouldn't have blades, you just have a disc, and it wouldn't move. So he did a bunch of math and figured out that the theoretical limit is 59.3%. Now that doesn't mean that a wind turbine's operating at 59.3%. It means that that's the theoretical max. By the time you factor in bearings and inefficiencies in the system and such, generally speaking, the amount of energy of potential energy that we capture is only between 10 and 30%. And you guys can stop me at any point if you have any questions, and I'll say I don't know. No. Okay, turbine math. Yay! No? All right. Subject to the Betz limits, there are three components that go into calculating the power in the wind. The wind speed, or the velocity, the swept area of the blades, and then the effect of elevation and temperature on air density. Who can tell me what the little symbol means, or what it's called? What's that? Rho, yay! It took me about 2 hours, yay! I couldn't remember. I couldn't remember, and it was like, well, how do you remember what you call a Greek alphabet letter when you don't know what it's called? Anyway, the formula to determine the amount of power is 1/2 of rho times A times the velocity cubed. Why do they build them in the sky? So the blades don't hit the ground. Ba-dum, boom. We'll be here all week. Actually, it's to avoid turbulence, and because generally speaking, the higher up you go, the faster the wind goes. Part of the reason for that is because of the friction that the ground causes. And then you got obstacles, buildings, trees, hills, that sort of thing, that cause the turbulence and cause the actual wind speed to slow down. So basically, it's to avoid that turbulence. Wind speed at height. Wind speeds increase with height due to the effect of friction, as I was saying. Basically, the ones that are lower to the ground interact with the ground itself and with the trees and such. The higher you go, the less friction you encounter. Also, if you think about it, air is really kind of like water. When you go down to the bottom of a swimming pool, okay, the water is a lot heavier, a lot denser there than what it is at the top of the swimming pool. That's because the stuff at the bottom has all the weight sitting on top of it. Exact same thing with air. So the higher you go up, the less density you have. Where is it windy? You notice down here in the bottom corner, there's a NIREL, National Renewable Energy Lab. If you're interested in this stuff, go to their website. I have it listed here in a little bit. Go to their website. It's just, You can spend days, weeks, months, years there. But basically, this is a map of the resources, wind resources in America, and where the transmission lines tie in. That's actually kind of an important thing because while it might be really, really windy up in North Dakota, there's not that many transmission lines up there. So, it's kind of like putting a billboard out in the middle of a farm field. If nobody sees it, if a tree falls in the woods, did it really fall? Okay. One thing I do want to point out here is that on the power cert classifications, you'll see that it starts with the white, goes to the yellow, a little bit, was it a kind of a mauve, and then into the red and the blue. The yellow areas is basically moderate, marginal, okay? But that basically means that, you're gonna get at least the 6.25 meters per second or 14 miles per hour. That's where they need to function. Every single state in the country has at least some small area that gets that kind of wind on a consistent enough basis to make sense of it. History of the wind as an energy source. Probably the first use of wind as energy source dates back to 4000, and this is something I learned, BCE. Apparently it's not politically correct to say BC anymore, but BCE, when the Phoenicians and the Egyptians first used sails on wooden rafts. Around 1 AD, the Greeks invented the first known wind machine powered by wind, and the first use of wind to generate electricity was in Scotland in 1887. The Russians built the first modern wind turbine. It was put into service in 1931 and ran until 1942. In the United States, 1941, the first megawatt-sized wind turbine was placed into service near Grandpa's Knob, Vermont. She got the joke. It ran for 1,100 hours before it threw a blade and was scrapped due to wartime materials. The reason why I point that out is it's not a new technology. A lot of people think that wind is, that all these wind, and they are high-tech machines by all means, but the basic concepts have been around for 150 years. Wind and the OPEC oil embargo. In response to 1973, the Organization of Petroleum Exporting Countries had an embargo where they got together and said, we're not going to sell you our oil. And everybody in the United States went, oh my God, ah! And if you go and read up on the time, I remember having to sit in line to get a tank of gas. You remember that? Yeah, it was a different time. There wasn't a 24-hour quick trip. But anyway, by the 1990s, the decreases in the energy prices had caused the energy to pretty much come to a standstill. It's very much the energy density of wind and all the renewables is less. And this is the first time in human history where we're moving from a more energy dense environment to a less energy dense source of energy. That's the first time this ever happened. Every other time, when they went from wood to coal's got a lot more energy in it, stored in it, than what the wood did. Now we're going to something that has less energy stored in it. Starting in the in the 1980s and spurred by rising costs and environmental concerns, people started looking at wind seriously. Various states, starting with California, they're usually the first out of the, they're the first in everything on this. Yeah, and they talked the federal government into encouraging wind and other renewable energy development. Since the beginning of the 21st century, commercial wind electricity generation has been growing by 30% per year. It's a growth industry. Unfortunately, it's been, if you look at the curve, on a piece of paper, it looks like it's been pretty much straight up. Unfortunately, there's a lot of zigzagging that goes on inside the curve. So right now, we're in a position where the production tax credit that is one of the subsidies that has spurred a lot of this development, they're more than likely not going to approve that for next year. Well, if you were talking about investing in a $100 or $200 million wind farm, you'd like to know that the government supports are going to be there. And it comes down to a thing where even right now, if they were to pass it today and say, okay, yeah, we're going to have it, so many things have been ramped down, so many projects have been shelved, that it would take another year or 2 or 3 to get back up to where we were at just a year ago. So politics does come into play. A lot of criticisms of wind. Have you guys heard any of these? What are some of the ones that you've heard?
They're ugly and they're loud.
Ugly, loud? Okay. Kill birds. Okay, cool. It's all true. I hate to tell you, it is actually true.
Is it loud and exciting?
Well, actually, that's
I learned they're loud. Aren't they getting quiet?
yeah, they have actually gotten a lot quieter. When they went from the 2-blade design, which were one of the ones out in Palm Springs that we were talking about earlier, those were real loud. I mean, because they're really chopping at the wind. Well, the 3-blade design, you don't get nearly as much. Plus, a lot of the noise from the older ones was from the mechanical things inside. But it is the set of the sails, not the direction of the wind, that determines which way we go. That's by a guy named Jim Rohn. He's my favorite business philosopher. You can change the set of your sails, but you can't change the wind. It's going to come from whichever direction when it wants to. But probably the biggest knock you'll hear about wind energy is that it's intermittent. The wind doesn't blow all the time. Sometimes it blows, sometimes it doesn't. Sometimes it blows real hard, other times. Okay, that is true. There's no denying that. However, it is something that can be engineered around by beefing up the grid to where we can transfer energy. If the wind's not blowing in North Dakota today, it might be blowing in Southern California, or it might be blowing off the coast of North Carolina. If you build the grid beefy enough to where you can transfer those electrons across the country, you're going to have losses due to transmission, but the fuel source is free for all practical purposes. So even if you have to overbuild in your capacity to make up for the losses that you get in the transmission, it still makes sense to do. So is it really a concern? It's something that needs to be addressed, but it's not a deal killer. Noise, okay? Comparative noise for common activities. Threshold of hearing 0, a rural night background 20 to 40 decibels, quiet bedroom at night 35 decibels. Wind farm at 350 meters away, which is the minimum that you have to set it because the blades do throw ice every once in a while. So you don't want to necessarily be really close to one when it's icing. But 35 to 45 decibels. So as you can see, the noise issue really isn't that big of a concern. I toured a wind farm out in Central Oregon, and was standing. You'll see the picture, and I'll show you the picture in just a little bit. But it was a very windy day, and I was standing right beneath this wind turbine, and you could not hear the wind turbine over the rush of the wind past your ears. So there is some debate on low frequency sound, which I think that's still being studied. But from everything that I've read, and I do attempt to be objective. And just so that you know, most of my business is in solar. I went to school for wind, but my professional expertise is in solar. So I don't really have a dog in the fight. So I'm going to I'll tell you the good, the bad, and the ugly as far as I see it. Bird deaths. Who can say that word? Anthropogenic. Is that right? Okay, bird mortality. Buildings, windows kill 550 million birds per year. A lot of birds. Cats, 100 million. High tension lines, 130 million. Vehicles, 80 million. Airplanes, 25,000. We've had a rash of those. Have you seen in the news where the birds have been running into the airplanes here lately? Wind turbines, 28,500. Now, something else I want our practical boots on the ground experience. Every one of these big wind farms has a biologist that's attached to it. And every single bird, it doesn't matter if it has a heart attack and drops onto the wind farm, that's counted as a bird death by the wind farm. If it lands on their property, it's cataloged. So in reality, now, back in the days when they very first started this, I was talking about the lattice structures. That didn't make a whole bunch of sense because the birds like to build a nest in it right as the slice-o-matic's going around. The other thing is sighting. Sighting concerns when they decide to put one of these up. Right now there's a company, Wind Capital, that's wanting to put a wind farm down in Florida that's right on the migratory bird path. Come on, I mean, why tempt fate? There's lots of places that we can put the wind. Like I said, every single state has some place where you can put wind development. You don't necessarily have to put them somewhere where you're going to be tempting fate. Electromagnetic interference caused by wind turbines. It's for the most part been addressed, but a funny story that I read, there's an Air Force base somewhere out west in Colorado or Wyoming that one day it was kind of a foggy, nasty day, maybe a little bit of thunder showers in the area. And the guy looking at the radar screen, all of a sudden it looked like there was like 300 incoming airplanes. And it was like, DEFCON 3. It turned out that it was just a weird set of atmospheric conditions, and the 300 incoming planes were actually the wind turbines at the wind farm not too far away. But now it turned out that the radar system had basically been built in 1956. Okay, so they upgraded that. They've also insulated and used synthetic materials to kind of block the effects of electromagnetic. Anytime you have something that's going to be churning out megawatts of electricity, you're going to have some electromagnetic. It just goes with the beast. But if you can shield against it, in which they can. Again, on the wind farms, you see everybody walking around with their cell phones. You see everybody walking around with their, their earbuds in and everything. No one seems to be pestered by it. So my radar detector worked, so I was happy with that. Aesthetic impact of wind turbines. My big thing on the wind turbines, as far as them looking, is you got to put it in perspective. Okay. When my wife and I were driving from St. Louis to Oregon for me to go to wind school, when we saw the first ones, we pulled over and went, "Oh my God, they're beautiful. They're gorgeous." Now, when you got up there closer to the little town where we went to school at, there were like 3 or 4 wind farms right together, and hundreds and hundreds of turbines. At that point, you know what? They started to look kind of industrial. So beauty is in the eye of the beholder. So what I'm going to ask is that you put it in perspective. We need the power, so you can either have wind turbines or a coal-fired power plant. Which would you choose? Put it in perspective. Different types of wind turbines. Okay, there are basically 2 different types of wind turbines. There's big ones and there's little ones. Actually, there's an entire spectrum of them, but they basically cut it into 2 different categories. Above 250 kilowatts is a big one. Below 250 kilowatts is a small one. I actually kind of confused. I was thinking about redoing this slide because these are 2 different types of wind turbines. The one over on this side up there is it's a vertical axis, and I'll talk about it in a second. And the other one's a horizontal axis wind turbine. But let's go back to the big versus little. The little ones are generally used in residential, farming, commercial properties. They're generally on the customer side of the meter. You don't have, it's just not economical for a utility to go up and put up a whole bunch of 100 kilowatt wind turbines. Okay, they're going to put bigger ones up. So that will be on the utility side of the meter. If you have a farm and you're pumping water or you're using it to generate electricity so that you can watch American Idol, that's going to be on your side of the meter. A lot of times they actually do the off-grid applications where the people are not even connected to, but for the most part, the intermittent nature of wind gets in the way of small scale wind as a reliable power source. The small ones can have 2 or 3 blades, which are generally made of fiber reinforced plastic and that are guided into wind by the tail. They're designed to furl out of the wind when the wind gets too fast so that they don't hurt themselves. They have direct drive permanent magnet alternators, three-phase. They pump out three-phase AC. It doesn't matter how fast it's going to pump it out. It just changes the voltage of how much comes out. Depending on the application, they have different controls that they can be electronically manipulated into producing AC or DC. And they generally don't require quite as fast a wind as the big guys do.
What is
Sure.
furling?
Furling, basically, it's turning out of the wind. If the wind gets too fast to where it would damage the internal components, it's designed where by the size of the fins on there, where when the wind gets too fast, it basically turns it out of the wind so it stops spinning. Did that answer your question? Cool. Okay. Vertical access ones, the big advantage of them is that you can put all the heavy stuff near the bottom. The turbines, the gearboxes and all that sort of jazz. You can put it down near the bottom. You don't have to put it 300 feet in the air. You know, if you look at the weight of some of these turbines, when by the time you build everything into it, they're millions of pounds. And when you think about this big grass stalk up there with, you know, these heavy gearboxes and shafts and everything, I have a slide that shows the different components to go into it. That's a lot of weight. And then the bigger you go with them, when you're talking these offshore ones that have 6 megawatts of power, those are big machines. With the vertical access ones, you can put all that equipment at the bottom where it's easy to work on and you don't have to engineer around all that weight. There's two basic different kinds of the vertical access ones. There's the kind that cup, and if you think about it, if you look at this one and envision a 55-gallon drum sliced in half. You put it on a pole, it's going to catch the wind. When it does, it's going to spin. Anytime you get that spinning, you can generate electricity out of it. Low tech, low efficiency, but you can, I mean, if you needed something just to get a little bit of extra juice on a windy day on your off-grid thing, why not put one up? The Darius wind turbines look like the egg beaters. If you go back to that slide earlier, they can be very, very big, and they can be utility scale. They've had some problems with the material sciences that go into designing them to where those bent things don't eventually flex themselves to death. The other thing is they're not very efficient because at any one time, half of them's out of the wind, if that makes sense. So when this one's catching the wind, the other one, by definition, isn't catching it, so forth and so on. So it's kind of a whoop, 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 whoop sort of thing. Okay, here we go. What do these two things have in common? Any guesses? They're both robots. Basically, a wind turbine is a giant robot. They have sensors that go out into the blades that actually measure the stresses at any particular point in the blade that optimizes it to catch the most amount of wind. If there's something that goes wrong, you get a fault, it'll shut itself down. One of the funniest stories that I heard about this is a buddy of mine went to work for a wind farm. People would put $200 million into building this wind farm, and they were climbing up tower to read the measurements. It was broadcasting them wirelessly. So his buddies go you can climb up the stairs, and he's sitting down there in the pickup truck with his laptop, and by the time he says, okay, I got it. You would think somebody would know to put $200 million together to put a wind farm up would teach their people better than that. But basically, they are pretty much autonomous robots. Large-scale wind turbines are the other category, and this kind of goes into a little bit of the components that are involved. The big bulbous thing that you see at the top, that's called a nacelle. Inside of there, in anything bigger than a 2 megawatt, I could stand with the doors closed And I'm 5'10", so somebody who's like 6 foot, 6'1" would be able to stand up. So they're pretty big. You got the blades, of course. The blades attached, the hub bones attached to the, or the blade bones attached to the hub, and then the hub attaches to a shaft, which transfers the spinning energy, which turns a gearbox, which increases the spinning, which goes into a generator, generates electricity. It goes down the tower, off into the grid. Like I said, I already went into the thing with the newer ones with the blades that are automatically optimize themselves. I thought that was pretty cool. Here's some resources. WEA's got a lot of good information. North Carolina State has a lot of information. If you want some good objective things about some of the issues involved, because you'll hear people slam wind left and right, okay? Most of it is either untrue or a half-truth. The United States Energy Information Agency has got thousands and thousands of pages that go into the different controversies that go around with it. And then that bottom one, the National Renewable Energy Lab, definitely worth checking out. Here's my contact information. Feel free to give me a call or to drop me an email. If you do want to use any of the pictures, you're more than welcome to. Just give me credit. Any questions?
I do.
Sure.
Why did they make them so skinny? It seems like they'd be more efficient if they were wider blades.
This is from my understanding of it. Basically, they've tried wider ones, they've tried narrower ones. It all goes together, it comes to the point of where they're maximally most efficient over a long period of time. In certain wind conditions, a fatter, wider blade might come in order. Now, the other thing, it's a matter of perspective too. When you're standing back, those wind turbines there are probably, I don't know, a mile and a half away. So from this point, they look pretty skinny. But if you were standing next to one, if I was standing next to one, I might be able to reach the very top from the bottom to the top. So they're 6 feet wide, maybe even 7 feet wide. Depends on the size of the turbine. Again, they're getting much bigger. Land-based applications, the size does become a factor because they got to get the machines to the sites. And of course, this is another one, these people are so smart. There was a wind farm that they were building in Europe. I think it was in England. And there's a picture that they go to the town. They're they're taking the blades on these big trucks, and they get to the town, and it's got like a right angle turn. It hadn't crossed anybody's mind to drive the route, and they actually had to build a road around the town in order to get the blades to it. So, I mean, engineers are smart, but they don't think of everything.
Aren't they really, really large, the size of a football field, some of the blades? Huge.
Yeah, I would say even some of what are now considered fairly small ones, the 2 megawatt ones, those blades, I'd be guessing at the length of them. But yeah, they're, yeah. Well, yeah, you have to figure if you look back at the, let's see if we can get this thing to go back. If you look at like this one right here, if you see that blade there, that tower is 300 feet tall. So that blade there swoops down pretty low. I mean, probably, 200 feet of it. So like I said, that's how come they build them so high up so the blades don't hit the ground. Yes?
So did they find that having 3 blades made it more efficient?
Yes. And to cut down on the noise too, because the 2 blades were, really cutting into it. Here's a picture of a 1930s era wind turbine. It used to be out west, anywhere pretty much across the country, and you would drive, and there were hundreds of thousands of these things. Most of them were used for pumping water in the Great Plains. These are some of my cohorts. As far as jobs in wind, everybody in that picture, with the exception of the guy with the t-shirt on, has gotten hired. I don't know what that says, but this is the picture of the wind turbine that I was talking about, where I was standing right beneath it. That was a very windy day, and I was that close to be able to take that picture, and you could not hear the blades. You couldn't hear them at all over the rush of the wind by your ears. This has nothing to do with wind. I just thought it was really cool. My wife and I were just out on a walkabout one day taking the dog out, and we followed this little sign to a park, and we found this thing down at the bottom of this ravine. It was at Whitewater Falls? Yeah, Whitewater Falls, Oregon. It was an old hydroelectric plant dating back to 1910. So again, renewable energy has been around for a long time. This is actually, you probably won't ever get to see something like this unless you do get into the energy. You saw the old version of the hydroelectric plant. That's the inside of the Dalles Dam. Have you ever heard of the Bonneville Power Administration? Okay, it's like the TVA, the Tennessee Valley Authority. They control the electrical distribution in the Northwest. This is one of their dams on the Columbia River, and I forgot how many turbines they had. I think they had like 13 turbines lined up. This one actually is the longest dam in the world. It's not the biggest by any means, but it's the longest. I mentioned the V27, the Vestas V27. That's the frame that it was built upon, and we completely disassembled it down to the frame and then put it back together. And let me. This was at a little school called Columbia Gorge Community College. When I got this wild idea to go back to school for renewable energy, there was only about 6 programs in the country that I could pick from. They were the ones that could get me in there soonest, so that's how come I ended up going out there. There have since, there are probably 100 now, and it's only been 3 years. But anyway, it was a class, and as you can tell by looking at the people, now the gray-haired guy in the middle, he's that's the instructor. His name is Alan Bailey. But I was one of the older guys, but we had one guy in the class that was 18. He was 18 when it started. So large part of a very various groups of folks to get into it. It's pretty much nuts and bolts on when you get down to the technology of it. Kind of looks like a truck frame. This I got a kick out of. It's kind of a little bit blurry, but if you see right here, it says, "Caution, before installing or operating, read instructions." Always good advice. That was on one of those. That was one of those. So always a good idea to read the instructions. This was a picture taken up at the White Horse Wind Farm near Ellensburg, Washington. Talk about weird atmospheric conditions. And then future grease monkeys in the sky. To give you an idea, that's the base of the tower, goes up 300 feet. That's about a 6-foot guy. So they're pretty darn big. So we need some more questions. Come on, beat me up.
So you're working in solar now?
I'm working in solar. When Kathy had to wear a hoodie on the 4th of July, we realized that they generally put wind turbines where it's cold and windy. And that pretty much nixed the old wind degree. They are, like here in North Carolina, though, they are talking about putting some, I forgot who, was it you that mentioned that the best one, probably the singular best place to put offshore wind turbines in all of America is off the coast of North Carolina. The water's shallow, so it's easy to work out there. The wind's consistent.
Maryland, Virginia.
Yeah. They've got one. There's only been one, and you might have heard about it on the news up near Cape Cod, that there was a whole bunch of, what they call NIMBY, not in my backyard. A lot of NIMBYism. Can you see them? Yeah, you can see them. I mean, but if they're 5 miles offshore or 3 miles offshore, they're going to be a blip, on your visual horizon. And then anytime when it comes to the argument about aesthetics, where do you want to put your coal-fired power plant if you don't want the wind turbines? Because
Unfortunately, you can't see the pollution, because if you could see the mercury and the pollution, I think it would be a different situation.
oh yeah, and that's one of the things also, and I don't want to get too political with it, but when you start talking, you'll hear people. Another criticism you'll hear is that wind doesn't pay for itself. That by the time you count in all the energy inputs that go into making the concrete that goes into the base, and the metal that goes into the tower, and the rare earth minerals that go into the generators, and all that sort of jazz. Now the payback is about 3 years on an energy produced versus energy consumed into it. But one of the things that, when they talk about grid parity, have you heard that term? Okay, grid parity basically is the holy grail that renewables is reaching, to where we can produce electricity with solar or with wind at a price that's comparable to what we have now on the grid, which is generally coal, natural gas. I say it like George Bush, some nuclear power. Actually, the nuclear power isn't. It's a lot more expensive than wind. But when you factor in the external costs that go with a coal-fired power plant, if you overlap where the emissions from a coal-fired power plant go, and you overlap a map of the cancer deaths, 1-to-1. It's a perfect correlation. You can even get uranium poisoning from living next to a coal-fired power plant. The ash, when you burn it, when you burn your fire in your fireplace, and after it's done, you have to scoop all that ash out. Tremendous amounts. Somewhere in Georgia, I think it was, that they had one where what they would do is they built these earthen dams, and they put the ash in a big pile, and then they'd spray it down with water, and it would get rained on so that it wouldn't fly away. They call it fly ash. And anyway, it filled up and the dam broke. What a mess. And it's not very healthy. They do have some industrial uses. They use it to make concrete, but the amount that they need to make concrete far is this much, and we have this much of the thing. But don't know if you believe in global warming, but there are those that don't.
This is the school of science and math.
I heard someone tell me once that, the temperature on Mercury has gone up 7 degrees. It's like, well, yeah, maybe it has, but no, it's pretty much, the science is settled there. By the time you factor in the external cost of the alternatives to renewable energy and to wind energy in particular, it actually, all costs involved, renewables are far cheaper when you factor it in. You had a question? In the white shirt? Or? Huh? All right, come on, make something up. No more questions? How about you? No? Nothing? All right, well, thank you very much for having me. I now know I need to add more slides. Again, my contact information's on there. If you have any questions, feel free to contact me. If I don't know, I'll shoot you in the right direction. And I appreciate you guys having me here today.
I have a question.
Sure.
What do you think is the best route for us who are going to college, who want to go into this kind of stuff? What should we do and how should we get involved? There
are a lot of different ways of skinning the cat. And it all depends on what your personal interests are. It's very engineer dominated. All of energy is engineer dominated because, basically you got a tiger by the tail when you start talking about megawatts of power. Yeah, it needs to be engineered. When you start talking about putting, something that weighs 600,000 pounds, 300 feet on the air on a base that's only, there's some engineering that goes into it. Energy is, like I said, 30% per year on the growth. Energy is a booming field. And it's not, if you objectively stand back and say, okay, is this going to die out again? In the 70s, after OPEC, it did come to a screeching halt, and a lot of people lost their shirts because they got into this and they thought this was going to be the wave of the future. Jimmy Carter put the solar panels up and then in the 80s, Ronald Reagan tore them right back down. This time, I don't think that's going to happen. It is kind of sort of happening on a small scale because of this whole political battling that they're doing with the production tax credit. But long term, if you look 5 or 10 years, 15, 20 years out, we'll use something that's topical. They're talking about bringing fracking to North Carolina. And they're saying, ooh, we got all this natural gas, let's go get it. Damn the consequences, let's go get it. Okay, well, let's put it in perspective. Let's say that at current consumption levels, let's be optimistic. Let's say that there's 100 years worth of our at current consumption levels, natural gas in the shale thing. All right. When you consider how quickly the rest of the world is adopting Western lifestyles, how quickly China is developing a middle class, how quickly India is developing a middle class, the consumption of this stuff is going to go up. They're talking about switching over a good part of the transportation fleet, particularly the big rigs, TJ, what's his name? Boone Pickens. Boone Pickens is talking about making all the 18-wheelers using compressed natural gas. I read a statistic, and again, it's just, I can't cite the source, but it seemed reasonable at the time that I read it, that if you put 10% of the transportation fleet into natural gas, that the price of natural gas is going to go right back up. Right now, you see utilities across the country that are saying, well, we're not so sure about the subsidies and everything we're going to get on the renewable stuff, so let's just go ahead and put a natural gas plant in. Okay, well, you get that when you start using natural gas as a base load provider, you're going to start burning a lot of natural gas. So between transportation, world demand, and using it as base load, I don't see what is now at this present point in time 100-year supply. What do you think an objective, realistic number would be on how long you think that's going to last with these things, with all these factors coming in? Let's say that it's 50 years. All right, well, that sounds like a long time. Okay, and to put it in perspective, I graduated high school in 1979. 50 years seemed a long time then, but it doesn't seem that long ago to me now. So when you think about it, it takes, if we wanted to, say, switch to hydrogen, just the sheer magnitude of the task of putting in hydrogen pumps in enough places around the country to where they would, where it would be usable and practical for everybody was going to take us 10 or 15 years.
You've got to make it cheaply, though. We don't know how to make it cheaply.
Yeah, that's the problem. Yeah, we got to hold it too once we get it. But so anyway, when you start talking about how to get into it or what the future's like, the future's so bright you got to wear shades. It really is. People will argue with you about peak oil. Are you familiar with that term at all? Okay. There are folks out there that says, oh no, the earth is manufacturing new oil. Yeah, well, technically that's true. The process is indeed still going on down there, but just not nearly at the rate we're going to need to meet our demand. So when you look at the fact that they're going after shale oil, by the fact that they're going after tar sands, by the fact that they're drilling, the Deepwater Horizon was, how deep was it going? Yeah, miles down. They wouldn't be going after this stuff if the easy stuff was still available. So whether you believe in peak oil or not, there are a lot of indications that it really is a problem, that it is something that within your guys' lifetime, definite, it's going to get really, really dicey as far as how much energy we have there. So, and then when you take into account the food production, that's something else that kind of gets involved with energy, because they use fossil fuel-based fertilizers. Okay, well, if you burn it all up in your cars, you're not going to be able to use it to grow food. So all these factors coming into play, ocean acidification. Are you guys up on that one? Okay, that's what actually got me into this. I read an article on ocean acidification, and people can argue about global warming, or climate change is the proper term for it now, I guess, but ocean acidification you can't argue with. You can take the whole issue of global warming or climate change and put it to the side and just look at ocean acidification. And when you consider that 85% of the the ocean's creatures spend some portion of their life cycle in the coral reefs, and the coral reefs are dying because the water has gotten measurably more acidic since we've been taking measurements, that's rock hard science. That's documentation. And if for no other reason now, and if you look at the percentage of protein production for human consumption that comes out of the oceans, it's a huge percentage. Now, it might not be for us here living in North Carolina or somebody living in Missouri or Illinois, but if you live in Indonesia, you eat a lot of fish. So when you take that, if you kill the coral reefs, you pretty much kill the oceans. If you kill the oceans, we're not that far behind. So while we'd like to bury our heads in the sand and ignore and wish and hope that it would go away, our energy problems are not going to go away. And eventually, if we don't fix it, Mother Nature's going to fix it. So I think there's a lot of potential there. How you go about doing it? If you're into math, there's engineering jobs out the wazoo. If you look on any of the job boards, renewable energy job boards, if you have an engineering degree and any kind of background, you can get a job. And one of the cool things about it too is if you want to travel, this stuff's worldwide. I mean, they're putting them in Africa, they're putting them in South America, they're putting them in Northern Europe, it's going everywhere. So, I always thought that would be kind of fun to, just go work in some places that are kind of exotic and that sort of thing. So I came to North Carolina.
Guys, it's true too. If you're interested in science, there's billions, literally billions and millions of dollars being spent in research for better photovoltaic cells, for better batteries. There's just so much research now looking at ways to cheaply get ethanol, from cellulose. That's huge. And this research is, cutting edge. There's so much opportunity.
North Carolina is a hotbed of that. You probably, if you wanted to run your car on biodiesel, Raleigh's probably one of the single best area because there's like 4 companies that manufacture it here. You can actually, you have a choice. There's like price wars on biodiesel here, and that's kind of a cool thing. Just today, they announced, I can't remember the name of the company, but there's a company in, is it Hendrick or Henderson? Henderson that just got named one of the top 10 most promising new technologies, and they are attempting. They have a solar panel that is running like 30% efficient, and the only other times that they've had that is like in the space program, and it costs $100,000 per panel. So and that's right here. I don't know how far away that is, but it's right here in the area. So yeah, there's a lot of different, the base science that goes into it. And then with the biofuels, they're doing some neat stuff with algae. Energy, like I said a second ago, energy and food production really goes hand in hand. When you slice that tomato up that you put on your BLT, unless you're a vegan, you probably would have told me about it already. But anyway, that tomato that you put onto your BLT sandwich might give you 60 calories, 70 calories for the entire tomato. When you count all the energy inputs that went into getting that tomato to your table, it has over 1,000 calories of energy encompassed in getting it to your table.
A lot more for the bacon.
Yeah, yeah. Oh, okay. Well, yeah, but the bacon tastes better.
Production of vegetables.
Yeah. So, but yeah, and beef.
Nutrition associated with production.
Yeah, yes, there is. Yes, there is. But yeah, so base science. I personally, I was in sales and marketing, and that's the angle I'm taking on it. So, you know, whatever turns you on and that you think would be of interest, it's going to be a booming industry. And if things go as I anticipate, it's going to really, at some point, they're going to have to get serious about it. And when they do, it's going to just be a boom industry. So.
Well, the military is serious.
Yeah.
I think they may actually lead us.
Yeah, yeah. The military's been probably, well, they have one of the biggest gas, energy bills of anybody, which is how come they have a practical thing. But yeah, they're not necessarily considered wild-eyed liberals either. And they're adopting this stuff. So, yeah. Anyway, any other questions? If you think of them, email me. I appreciate you letting me be here tonight. Thank you.